Let's do a little reviewing for our upcoming optimization and related rates test. So remember, the big idea for optimization is we need to find a primary and secondary equation. And all of that secondary equation means that's just helpful information to substitute. Then we'll solve the derivative equal to 0, set the derivative equal to 0 and solve it. Okay, well, let's see what happens. So we got a farmer with a fence in a rectangular pen. It's up against a building, so we got a building, and we've got a fence here. We know he's got 100 feet of fencing for 3 sides of the pen. Want to find the dimensions? Well, we've got, we can label this in different ways. You could use length and width. You could use X and Y. It doesn't matter. But a drawing's super helpful. And we want to maximize the area here. So we need our primary equation, the thing we're trying to maximize. That's area equals X times Y. And then we need something that relates X and Y. Well, that would be the perimeter equation. That 100 has to be 2x's plus y. And the whole idea is we want to take the derivative here, but we have 2 variables. Can't do much with the derivative if we have 2 variables. And so what we need to do is solve this equation for y and subtract 2x from both sides. We get 100 minus 2x. Now we can take that and we can substitute here, and we can now rewrite. We know area equals x times 100 minus 2x. And we're going to be taking the derivative here and setting equal to 0, so we might as well clean that up a little bit, distribute that x out. We've got 100x minus 2x squared. And now we can set that equal to 0, the derivative that is. So a prime is 100 minus 4x. We want to set that equal to 0. And if we subtract 100 from both sides, 100 equals negative 4x, and so x is 25. The question is find the dimensions. So we're halfway there. Make sure you always go back and check to see what the question was asking. So we found one of the dimensions, 25. If we plug that back in here, we have 100 minus 2 times 25, so y equals 100 minus 2 times 25, which is 50. So our final answer is 25 feet by 50 feet. That gives maximum area. Now double check, it didn't ask us for the area, I don't think. Let's see. So give him a maximum area. So find the dimensions. Yep, didn't ask for the area, so we got it. Great. How about this one? We want to find a point on the graph of this equation that is closest to 3, 5. All right? So we've got this parabola going on here, and we've got a point, and we want to find the distance from it. So we can sketch it. X plus 2, if you remember, this moves left 2. All right, just to give us an idea of what's going on. All right. Okay, and we got some point 3, 5 over here somewhere. And we're trying to find a point x, y on this graph that is closest. So we got to find the distance between these two. So we have to use the distance formula. The distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. All right? We'll find the distance between these two, x and 3, y and 5. So we can rewrite that as the square root of x minus 3 squared plus y minus 5 squared. Well, we want to take the derivative here because we want to minimize this distance. We want it to be closest. That means the minimum. So we need a secondary equation. Well, our secondary equation is the equation that was given to us, y equals x plus 2 squared. So we're going to plug that in, and we have the derivative, distance, d for distance, x minus 3 squared, and we can swap out this y for x plus 2 squared. That's all going to be in parentheses, minus 5 squared. So we got a pretty crazy looking equation there. Now we probably could solve this. Now this will be a calculator test. So we know we need to find the derivative of this. So we can go to our TI Inspire and find our derivative here. So here we got our calculator. And let's see what we can do here. So we're going to our TI Inspire. Now this is on the app, so it looks a little differently, but same idea as your calculator. So we want to enter our equation for the distance, and I'm going to go ahead and call this f of x. Okay, and we're going to store, so we need our colon equals, and we're going to do square roots. You could call this d of x if you want, but since we use the d for derivatives, it gets a little bit complicated there. So we got x minus 3 squared plus, careful with your parentheses here, and we're going to have x plus 2, that was the y equation, squared, minus 5, close that parentheses. Let's see, I missed a parenthesis back here, didn't I? There's a parenthesis there. There we go, and we want that to be squared. Double check, make sure you typed in everything correctly, and we did. So there it is. So we're going to go ahead and find the derivative of that. So you go to your, I got a shortcut here, but under Menu, Calculus, you'll find the derivative. And we're going to set the derivative. Let's see. So the derivative of f of x, there we go. Okay. And there's that whole thing there, all right? Pretty ugly. You see why you don't want to do it by hand, okay? So you don't even really need to write that down, okay? So what we're going to do is we're going to say we want f prime to be equal to 0, and that's something that you'll need to write down on our test and in the AP test. So we're going to go ahead and solve that. So we'll go to our menu, algebra, and we'll go to solve. And what we want to solve is we want to set the derivative equal to 0. So we're going to go to menu, calculus, derivative. Okay. And the derivative of f of x. Okay, so there's our derivative of f of x, get out of the parentheses, equal to 0. So we want that to be equal to 0, and we're solving it, comma, for x. Don't forget that comma x. Okay, so what it's going to do is it's going to go ahead and find that derivative. It's going to set equal to 0, and it's going to solve it. All right? Again, something we don't want to do by hand. So there you have it. We've got a couple negative values, and we've got this positive value. And the question now is, all right, which one is the smallest distance? Okay, and we can find that out. Let me show you real quickly how we find that out. You could probably guess that it's the positive one because that's going to be closest. But if we do f of, and you can copy and paste those values, but we just want to get a pretty good idea. There's f of negative 3.75, and that's a distance of about 7. And so we have f of, what do we got there? Negative 2.605, rounding off correctly there. Okay, so that's about 7.27. And then we have f of, and 0.358. And that's going to be much smaller. All right, so we could kind of guess that it was that third one, but we really should check all three. These are critical values. So we found critical values. A couple of them are larger ones, and the the smallest one would come from 0.358. Okay, so the distance there is 2.7073. Now, we need to find the y value of this. So remember the y value, the equation for this was x plus 2. Now, you can come up here like this, and you can copy. All right, so I go like that. I can pull that number down, or you can just type it. But it was x plus 2 squared. That was our y value. All right, and so there's our y value, 5.56. And that's going to be 5.560. And that's going to be our final answer. So the closest point, that's what the question was asking us for. The closest point would be, our x-coordinate was 0.358, and our y value was 5.560. Okay, there you have it. All right, again, when you're showing your work, you're going to use your calculator for this. You should probably write something like this. Okay, d prime equals 0. So there needs to be some evidence that you took the derivative and set it equal to 0. You don't need to work it out. Okay. Well, let's look at one more here. And we have a rectangular prism has a base that has a length that is twice the width. All right, so we have let's say we've got a width of x, so this is 2x. If the maximum area of the box is 200 square inches, the surface area, find the dimension of the box that will maximize the volume. Now notice that there's another dimension it hasn't told us about. So we don't know what this dimension y is here. So we've got to put that in. It doesn't tell us it's a square or anything like that. So let's make an equation here. We've got a volume, which we're trying to maximize the volume. Volume is length times width times height. That's something that we should know. 2x times x times y, or 2x squared times y. Now we also know something about the surface area. Okay, the surface area is 200 square inches. This will be our secondary equation. Let's get a different color for that. So 200 equals, now there is a surface area formula for a box here, but we just need area of all the faces. There's 6 faces. We should be able to find them all. This face on the right here is x times y. That's the area. There will be 2 of those. 2 times xy. There's one on the right. There's one on the left hiding back here. We've got this face on the front. This is 2x by y. So this rectangle on the front is 2xy, and on the back is 2xy. So we need to add 2 rectangles that are 2xy. On the top, or bottom, we have a rectangle here that is 2x times x. The top is 2x times x also. So we have 2 rectangles that are 2x times x. So if we clean that up a little bit here, we have 2xy plus 4xy plus 4x squared, and that equals 200. We can go a little bit further here. We've got 6xy plus 4x squared. There's our secondary equation. So we got our 2 equations. We've got our volume equation, and we've got a helper equation, or sometimes we call it the constraint equation. Secondary equation. That's there. Okay. Now, we want to find the derivative of the volume. The problem is we have 2 variables. So we need to solve this for y. So let's go ahead and solve this for y. Let's subtract over the 4x. 204 minus 4x squared, that is, equals 6xy. And let's divide both sides by 6x. And y equals 200 minus 4x squared divided by 6x. Now we can take that and we can substitute that for y. And that gives us a new equation, v equals 2x squared times 200 minus 4x squared all over 6x. Okay? And we can go right to our calculator right now with this to find the derivative, or we can simplify it a little bit. If it's easy to simplify, you might want to do that. You decide. Sometimes I like to simplify it so that I don't make as many mistakes when I type this in the calculator. The less you type, the less chance there's mistakes. So 2 goes in there once, 2 goes into there 3 times. This x cancels with one of those x's. We still have an x left, so that x needs to be distributed there. So v equals 200x. Notice the whole denominator canceled there, 4x cubed. Okay. Now, if you are nervous about making a mistake on that simplification, then probably should go right to the calculator there. But I think we got it pretty good. Double check. We entered this equation right. 2x squared times that fraction, 2 and 6, leaves us, oh, wait a minute, we got a 3 on the bottom. See? Good idea there. Good thing that we checked. Okay, so that's all over 3. There's still a 3 on the bottom. All right. Now we can go to our calculator and solve this. Well, you know what? So you can take this to your calculator. I'm going to go ahead, since this is just divide that by 3. This is 4/3 x cubed. Let's go ahead and find our derivative here. Our derivative, we get 200 thirds minus, let's see, drop the 3, we get 4x squared. Okay, that's not too tough. All right, so for sake of time, if this is a calculator, since this is a calculator test, if you want to write this down and use your calculator, you can. Let's go ahead and calculate it real quickly here. We've got negative 4x squared. Subtract 200 from both sides, 200 thirds. Multiply by, or actually divide by negative 4. And so x squared equals, if you divide by negative 4, you're going to get, let's write like this. Negative 1/4, the same as dividing by 4. Okay. And that's going to leave us with, cancel those out, that'll be 50. So we'll have 50 thirds. And we'll square root, and we got our answer. And getting our calculator out for this, we get about 4.082. All right. So that is x. Now we've got to go back and check. That's not the final answer. The question, well, it's partly the final answer. The question was to find the dimensions of the box that will maximize the volume. We found the x. We can find the rest using this information here and the fact that it's 2x. So our dimensions are 4.082 by double that. And if we double that, now we want to double this on our calculator. So when you take that answer and double it on your calculator, we're going to get, it actually rounds to 8.165. Okay, because this was rounded. So don't double the rounded answer, double the actual answer in your calculator, okay? Or I guess you could write 2 times the square root of 50 thirds, okay? And then our y value, we're going to take this and plug it in here. So to find our y value, we've got to plug this into here. So y is going to be 200 minus 4 times 50 thirds squared, the square root of 50 thirds, it's a square root there, all over 6 times the square root of 50 thirds. All right. And let's see what that comes out to be. And that comes out to be about 5.443. All right. There's our final answer for the dimensions of the box with the maximum volume. So once again, we get a primary equation, the thing that we're trying to maximize. We get a secondary equation, or equations, might be more than one, that allows us to substitute. Okay, and then from there we can substitute, find the derivative, and set the derivative equal to 0 like this here, and then use that to get our final answer. All right, and that will give you the value that is the maximum or the minimum. All right, and that's how we optimize. Now let's get into some related rates. So in related rates, we need to come up with an equation. Well, first we need to figure out the variables that are changing, make an equation that relates the variables, take the derivative with respect to time, or t, and then solve the equation using the information we know. All right, so what do we got here? We've got a right triangle, so we got the longer leg of a right triangle, and it's shrinking at 2 inches per second. All right, so that's let's get some labels here. We've got maybe x, y. All right, and so if x and y, we know that y is shrinking. So that's dy dt. That's the rate of change there at -2 inches per second. Units are important here. Okay. Now we've got a shorter leg of the triangle is shrinking at 1 inches per second. All right, so the short leg there, call that x. So that's dx. Oops. Let's go dx dt, and that's -1 inch per second. We want to find the rate of change of the hypotenuse when the longer leg is 10 inches and the shorter leg is 7 inches. Okay, now this is our snapshot in time, so we'll just hold off on that for the moment. First thing we need to do is we need to relate the variables, the things that are changing. All right, and so we need to label this hypotenuse. Let's call that C maybe. All right. And so we have x squared plus y squared equals c squared, our Pythagorean theorem. So anytime we've got a right triangle in the mix, Pythagorean theorem is probably where we're going to go. So we need to now get an equation that has dy dt in it and dx dt. Notice there's no rates of change in here. This just relates the variables, not their rates. So to get a rate equation, we need to take the derivative, and that is the derivative with respect to time. So we're going to take the ddt of both sides here. Got to do the whole thing, and then we've got to do that implicitly. So the derivative of x squared is 2x, but we're doing this implicitly, ddt, so we're going to have the derivative of the inside dx dt plus derivative of y with respect to t. Well, we got to find the derivative with respect to y first. That's 2y times dy dt. And the same thing on the other side. Derivative, start with the outside. Derivative with respect to c. That's 2c times dc dt. Okay. So now we can plug in everything we know. So at this snapshot, at this moment of time, we have the shorter leg is 7, the larger leg is 10, and we need to find the hypotenuse here. Well, that's going to be 7 squared plus 10 squared square rooted, and that's going to be the square root of 149. Leave it exact is good. So let's go ahead and fill in everything we know here. So we have 2 times x, which is 7, times dx dt, which is -1, plus 2 times y, which is 10, times dy dt, which is negative 2, equals 2 times c, which is square root of 149, times dc dt, which we don't know. That's the thing that we're trying to look for there. So cleaning this up, we get negative 34 equals 2 square root of 149 times dc dt. And dividing on both sides, we get our rate of change for the hypotenuse, dc dt, equals negative 34 over 2 square root of 149. And so that's exactly negative 17 over the square root of 149, which is approximately negative 1.393. And don't forget your units. Our units are going to be inches per second because this was all measured in inches and the rates were in inches per second. So now we got a problem with a volume of a sphere. So we got the radius of a sphere is increasing at 3 inches per second. Find the rate of change for the volume, which is given an equation. And we got a radius of 6 inches is our moment in time. So volume equals 4/3 pi r cubed. And we're told here that the rate of change of the radius is increasing, so it's positive. If it was decreasing, it'd be negative 3 inches per second. So let's go ahead and get our derivatives in here. So we need to take the derivative with respect to time. So we have dv dt equals, now we got to do the outside first, derivative with respect to r first. So drop the 3 down. 4/3 times 3 is 4 pi r squared. And then we're going to multiply that by the derivative of the inside, dr dt. And now we're ready to plug in things we know. So dv dt is equal to 4 pi times the radius. Well, we want this at a radius of 6 inches squared times dr dt, which is 3. And that comes out to be 36 times 3 times 4 gives us 432. And this is a change in volume, which is cubic inches per second. It's cubic inches because we have inches times inches here times inches per second. All right, that's it. That one's pretty straightforward. All right, one more here. We've got a man walking that's 6 feet tall, walking 3 feet per second, walking away from a light that's 18 feet above the ground. When he's 12 feet away from the base, what is the rate of the tip of the shadow moving? Okay, so we've got this situation here. We've got a light up here. Let's get our light going. Here's our light bulb. Okay, light bulb shining down on this guy that's walking here. Very long torso there. All right. And so the question is, what is the rate? Well, we know we got his rate here. So let's maybe call that x. So his distance from the base of the light. And then we have the distance to the tip of the shadow. Okay. And so we know, what else do we know here? We know that the light is 18 feet above the ground. We know he is 6 feet tall. And we know he's walking at a rate, so that using the variables I just picked there, you can pick different variables, of course, is dx dt is 3 feet per second. Okay, and we're trying to find dy dt there. The key here is we have some similar triangles. We've got one triangle here that is similar to this triangle here. So the gray triangle there is similar to this little blue triangle. And so we can make a proportion, but we're going to need one more side in this small triangle, and that would be this. And so we could pick a different variable, but we want to kind of keep the variables the same probably. So this would be y minus x. Y is the whole distance. X is that short distance. There we go. All right. So let's make a proportion. We know the rise and the run has to be proportional to the small rise and the run. So the big rise, 18, over the full run y is equal to the small rise, 6, over the short run y minus x. You can make this proportion different ways. You could say 18 is to 6 as y is to y minus x. That would also work just fine. Well, if we clean this up a little bit, let's cross multiply. 6 times y equals 18 times y minus x. And so we have distribute that out. And subtract 6y over, add that 18y or 18x over. There you have it. Okay. We're looking for the change in y here. So if you want, we can even go ahead and go one step further, divide both sides by 12. 18 twelfths is 3 halves. And now we can find the, remember we're finding this implicitly. We need the derivative with respect to time here. So d dt. So we have 3 halves. The derivative of 3 halves x is 3 halves, but then we got to multiply by dx dt, and that equals dy dt. The derivative of the right side is just dy dt. All right, well, we know dx dt is 3, so this is going to say dy dt is 3 halves times 3, which is 9 halves. And our units here will be, let's get rid of this here. Our units will be feet per second, right? So this is feet. Don't forget your units. Feet per second. And there you have it. So the big idea for related rates, once again, the main steps. We've got to figure out the variables. And often that includes making it a drawing to help us out. Then we can make an equation that relates the variables, or sometimes that's just a formula like this, or a proportion here. Sometimes we want to clean that equation up a little bit first. Next step is to find the derivative with respect to time. And then the next step, once we got that derivative, is to substitute and solve for what we're looking for. Substitute and solve. Substitute and solve. And that is a process of solving related rates problems. So keep at it, and hopefully that helps. Thanks a lot.